Hey, everybody, welcome back. We are starting chapter 7, and chapter 7 is all about confidence intervals. And I wrote a little introduction here to sort of introduce us to what a confidence interval is. And we're going to start out with a scenario. Suppose you want to start your own coffee shop. You need to know how much the startup costs will add up to, at least on average. To start with, you ask others who have started their own shops, and you find they have a mean or an average of $30,000. But you know it might not be exactly $30,000 for all coffee shops. Based on your data and some statistics, you think it could be off by as much as $10,000. This, by the way, is what is referred to as a margin of error. Now, this margin of error, we often use the capital letter E to represent that. You'll see that in formulas and things like that. So if it could be off by up to $10,000 in either direction, then what I'm going to do is I'm going to take $30,000 and subtract $10,000. So that means it's going to be between 20,000. And I'm going to take 30,000 and I'm going to add 10,000. That's going to be 40,000. So this is our interval that we are confident in. So we're fairly confident that the true startup for my coffee shop is going to be somewhere between $20,000 and $40,000. And of course, the more data that you get, the more accurate you can make your confidence interval. And let's move on and talk about exactly what we mean by this. And you can see in the box that we have here, this is an interval that we are confident, at least to some extent, contains the value we're interested in. Now, this was just us sort of spitballing this. So let's go into a little bit more precise. And when I say precise, none of it's precise. It's all approximations. A little bit more mathematical way of doing this. So here are some confidence interval concepts. The purpose of a confidence interval is to estimate some value from and the correct answer here is some value from the population. Now, we are going to end up with a confidence interval of either the mean, the true proportion, or the population standard deviation. These are going to be the three different types of confidence intervals. This particular video, we are going through section 7.1 through 7.3. So that's going to cover the mean and the proportion. There's a different video for the standard deviation. All right, let's keep going. A confidence interval is reported as two numbers, just like we had up here, 20,000 to 40,000. We think the population value is between them. To construct a confidence interval, we need a starting point called a point estimate. And for our purposes, that is going to be the sample version of each one. So there's the sample mean, sample proportion, and sample standard deviation. So those are going to be our point estimates. And we are going to need a margin of error. In our previous example, our margin of error was that $10,000. The point estimate is the center of the interval, and we add and subtract the margin of error to create the interval. So that's what we're going to be doing here. Next up, because the confidence intervals are based off of random samples, and this is really important, we are confident. We never know for sure. Statistics is never about knowing for sure. It's all about probabilities. How close do we think we are to the true value? Because confidence intervals are based off of random samples, we are confident the population value is contained in the interval. Our confidence level will be based on a percentage. For our purposes, this is going to be given to us as a math problem. They'll tell us the confidence level. When you're really in the field and things like that, you'll have to decide what the best confidence level is for your specific experiment. So 95% confidence, we could put 99% confidence and 90%. These are the three most common ones. In statistics really means that if we create many confidence intervals, about 95% of them would contain the actual population value. Based off of these concepts, the correct interpretation of a confidence interval would be that we are some percent, I'll just make one up, 95%, confident that the true proportion, or the true and then population value, again, this is the mu or the p or the sigma. So the true population mean, the true population proportion, or the true population standard deviation, and is between some minimum value and some maximum value. So that, in a nutshell, is what a confidence interval is. And we are going to move on to section 1. Part 1, estimated population mean. Now, this is important that we highlight this. In this case, sigma is known, meaning the population standard deviation is known. And if it's known, that means that we are going to be using a z distribution. Also known as a normal. So we're going to be using our inverse norms and our normal CDF and things like that. All right, we're going to start with the confidence level. Is the probability that the confidence interval actually does contain the population parameter. Again, that's the mean, the standard, the proportion, or the true standard deviation, assuming that the estimation process is repeated a large number of times. All right, so let's talk about the most common confidence levels. Our most common, as I mentioned before, is going to be the 90%, the 95%, or the 99%. And again, you may be asking yourself, why wouldn't we always try to do the 99%? Sometimes it just isn't practical to do that. We don't have enough data, or we don't have access to enough data, or it's too expensive to get the data that we would need to do that. Now, the corresponding alpha is going to be whatever is left out of the 100%. So if our confidence level is 90%, that means our alpha is 10%. Now, something that we're going to need in a few minutes is our alpha divided by 2. And half of 10% is 5%. For a 95% confidence level, we're going to end up with alpha equals 5%, which means our alpha divided by 2 is half that, which is 2.5%. And when our confidence level is at 99%, that means our alpha is at 1%. And our alpha over 2 is going to be half of that, which is 0.5%. Be careful with that one. You have to put 2 zeros in front of the decimal to make it that. Otherwise, if you just put 0.05, then you're looking at the very top one there that you see. All right, let's move on to our critical value. A critical value is a number on the borderline separating sample statistics that are likely to occur from those that are unlikely. The number z sub alpha over 2 is a critical value that the z-score with the property that is that separates an area of alpha over 2 in the right tail of a standard normal distribution. Notice this is going to be in the right tail, meaning we're always going to be looking for the positive version of this. All right, let's talk critical value. So when we have our confidence level at 90%, again, that means our alpha is at 10%, which means, again, alpha over 2 is 5%. And so z sub 0.05 is going to be inverse norm of 1 minus 0.05 because we want the right tail. And remember, inverse norm only knows area to the left. So let's get into our distribution. Inverse norm, 1 minus 0.05. So this is about 1.64485. So 1.64485. And we'll continue with this. Alpha is now 5%. At a confidence level of 95%, alpha is at 5%, which means alpha over 2 is 2.5%. And that is going to be inverse norm 1 minus 0.025. It's going to be about 1.96. Everything's rounded off. So 1.96. These are common critical values when we're dealing with a z distribution. When we get to the t distribution, things are going to change. So at 99%, alpha is at 1%, and alpha over 2 is 0.5%, which means z sub 0.5% is inverse norm 1 minus 0.005, which is about 2.5758. So it's good to know how to find these critical values. Even if the same ones pop up, it's still good to know how to find them. All right, let's get to our first confidence interval. Finding a confidence interval with sigma known, so this is, again, a z distribution. Number of farms. A random sample of the number of farms in thousands in various states follows. Estimate the mean number of farms per state with a 99% confidence. And here's the big key. We're going to assume that sigma is 31. Now, what I'm going to do is I'm going to have you put in your calculator into list 1 the data. Sorry, I ended up with an advertisement here. And there we go. Now you'll notice my list 1 is this list here, 7, the 68, the 16, and so on. So you may need to pause the video to put the data into your calculator so that we can work this. We are going to use a z interval. And that is found under stat, test, and then z interval. So let's see. So I'm going to hit stat, test at the top, and I'm going to scroll down till I get to z interval. There it is. And sigma is 31. You can see the yellow highlighted there. My data is in list 1. Frequency, just put a 1. And my C level is 99 in this case. And then we just hit go, and it spits out the answer for us. There it is. So here is our confidence interval. So it says round well, we'll just here, 30.885 up to 64.933. And these are in thousands, numbers of farms in various states. So we can be 99% confident that the true mean is between 30,885 farms in a state and 64,933. Now, I know you see a decimal there, but just remember all these things are in thousands as we're looking at this. And to be clear, this is the final answer right here. All right, next step, we're going to be introduced to a new formula. If we want to find the sample size for a mean, first of all, this only works if we know sigma. So sigma must be given to us for us to be able to do this, or a way to find sigma, meaning the true population standard deviation. And here is our formula. This is not particularly difficult to calculate or to get this formula, but just to read this to you, this is z sub alpha over 2, so we're going to have to calculate that, times sigma, so again, sigma must be known, divided by a known error. So I want to take a look at our actual problem here, and I want to read it and pick out the bits and pieces that we have, and then use our formula. Water temperature. If the variance, now we're talking variance, but that's sigma squared, of water temperature in a lake is 26 degrees, that means that our sigma is the square root of 26, just to be clear. How many days should the researchers select to measure the temperature to estimate the true mean within 4%? So that's our E, 4 degrees, not percent. Within 99% confidence. Now, let's break that down. 99% confidence, so we call that our C level. Now this means our alpha is 0.01. Alpha over 2 is 0.5%. And z sub 0.005, once again, is going to be inverse norm. 1 minus 0.005. And let's calculate that out again real quick. All right, so we have second inverse norm. 1 minus 0.005. So I'm going to use this as part of my computation, 2.5758. So using the formula in black above there, n is going to be 2.5758 times sigma, which we have up here. That's the square root 26 divided by E, which was 4 degrees. We're going to square that whole thing. So I'm going to square the 2.5758. Actually, I'm not. Let's do this. 2.5758 times the square root of 26. Make sure you get outside of the radical, divided by 4. And now I'm going to square the whole thing. And we always round up. So this one's 10.7, so we would round up anyway, but even if it wasn't, we would still round up. So this is about 11 days. Hope we're doing okay. I want to move on to part 2. The t-distribution. This is if sigma is not known. Then we use a t-distribution. If sigma is not known and a population has a normal distribution, then we have t is equal to x bar minus mu divided by sigma, or not sigma, s divided by root n. And that's all about the central limit theorem. All right, so if sigma is not known and a population has a normal distribution, then t equals x bar minus mu divided by s divided by root n is a t-distribution. T-distribution. So we are no longer using z. We're now using t for everything. For all sample of size n. Now, the difference with a t-distribution is the t-distribution completely depends on n, whereas a normal distribution does not. And we still need to find the critical value. This is now t sub alpha over 2. It can be very similar to what we just did. Requires a value for the degrees of freedom. Degrees of freedom are sort of like our wiggle room. We often refer to degrees of freedom as df. In fact, from now on, I'll probably usually just write it as df. And for a t-distribution, that's going to be n minus 1. And we're going to construct a confidence interval used to estimate the population mean without sigma known. The requirements: the sample is a simple random sample, and the population is normally distributed, or n has to be bigger than or equal to 30. Meaning if we don't know if it's normally distributed, or we know that it's not normally distributed, n has to be bigger than 30. And here is our confidence interval, x bar minus e and x bar plus e. This is where e is defined as t sub alpha over 2 times s divided by root n. And our degrees of freedom, again, is n minus 1. All right, let's talk about some properties of a t-distribution. A t-distribution is different for each sample size, meaning as n changes, the distribution changes. A t-distribution has the same general symmetric bell shape as a standard normal distribution. T-distribution has a mean of 0. The standard deviation of the t-distribution varies with the sample size, but is greater than 0, meaning it's always positive. When a sample size n gets larger, the t-distribution starts looking like a z-distribution, a standard normal distribution. So when n is like at 1,000 or something like that, then you could use either the t or the z. It's the same. So let's find a confidence interval at the 95% confidence level for the mean based on the camera prices below. So we have our C level is at 95%. And to be clear, this means that alpha is 0.5. And before we start getting into all of that, this data that you see here, I have already loaded into my list 2. You can see it there. It's with the 222 and so on. So you may need to pause the video to put that into your list, but mine is going to be in list 2. And what we are going to be running in this case is a t interval. Which can be found in the same place as the z interval. So I'm going to go here, stat, tests. I'm going to scroll until I get to the t interval. My data is in list 1, and then they just need my C level, which is 95. It's still 95, so we're good. So we hit calculate, and we are done. Oops, I didn't change it to list 2, sorry. So that's a good lesson there. Make sure you change it to the right list. So second 2 is list 2. And there we go. So they are saying that, and let's keep the purple, why not? That we are between $189.12 and $233.38. And that is our actual confidence interval. So we're saying the true mean of these cameras with all these specifications, the 6 megapixel and the optical 3x zoom, I don't know what any of that is. And we have the prices down here. So the true mean is going to be between $189.12 and $233.38 based on the data that we have here. All right, we're going to do one more example. Hospital noise levels. For a sample of 8 operating rooms taken in a hospital study, the mean noise level is 39.2 decibels, and the standard deviation is 11.2. Now, I want to point out, it says standard deviation, and I want to make a list here. So X bar is 39.2, and our sample standard deviation is 11.2. So even though it says standard deviation, we don't know the population standard deviation just on the sample based on these 8 operating rooms. So here's our information. Find a 90% confidence interval with the true mean noise levels of operating rooms. All right, now I want to point out that our C level is at 90%. Once again, we're going to be using a T interval. So stat tests, we're going to go down to a T interval. And we are no longer using data, we are using statistics. And I obviously practiced with this one before. We already have the X bar is 39.2, SX is 11.2, and in this case is 8. C level is at 0.9. And here we go. And there is our confidence level. Confidence interval, pardon me. So we're getting 31.698 and 46.702. And that is our actual answer there. So we are 90% confident that the true decibels, this is in decibels, is between 31.698 and 46.702. All right, one more section. So far what we've done is mean with population standard deviation known, that was a Z interval. Then when the population standard deviation was not known, then we used a T interval. And now we're going to talk about estimating a population proportion. Population proportion. Definition, confidence interval for population proportion P. When data from a simple random sample are used to estimate a population proportion P, the margin of error referred to as capital E usually, is the maximum likely difference between the observed sample proportion, in this case, that's going to be p hat, and the true value of the population proportion, which is just p. The margin of error is going to be, as I mentioned, capital E. It's going to be z sub alpha over 2. By the way, proportion ones are always based on the standard normal, the z distribution, times the standard deviation, which is p hat q hat over n. And to be clear, q hat is the complement of p hat. So the confidence interval for estimating a population proportion, P, is going to look like this. P hat minus our margin of error, P hat plus our margin of error, and where E is defined above. The requirements, the sample is a simple random sample. There is a fixed number of trials, and the trials are independent, and NP and NQ are bigger than or equal to 5. All of those will be met for our problems, no problem. All right, travel to outer space. A CBS News New York Times poll found that 329 out of 763 randomly selected adults said they would travel to outer space in their lifetime, given the chance. Estimate the true proportion of adults who would like to travel to outer space with 85% accuracy. All right, let's identify what we have here first. Let's go back to purple. This is going to be our x, and this is going to be our n. And p hat is going to be x divided by n. The good news is the problem is going to do all of this for us. All right, so we are going to use stats, tests. This is going to be a 1 proportion z interval. So I'm going to go ahead and find that. So I'm going to go to stat, tests. I'm going to scroll down. Now, be careful. There's 1 proportion z test. We'll use that in the next chapter. But for now, we're 1 proportion z interval. There it is. It wants to know x. X in our case is 329. It wants to know n is 763. And our confidence level is 85%. That's somewhat of an unusual one, but we can handle it. And then calculate. And there we are. Done. We love our calculators. Sit around to 3 decimal places. All right. So this is just a matter of knowing which test you need to run or which interval test you need to run. Some calculators may be in a different place. If you have a Casio, it might be a little different. But it's all there for sure if you have a graphing calculator. Okay, so let's be a little more specific if we want to find the sample size now, meaning I want to know how many data points I'm going to need to guarantee a certain whatever. So here I want to point out, what we're looking for here is we want to know what n is going to be. So when an estimate of p hat is known, then the formula is here. And remember, q hat is 1 minus p hat. Now, if we don't have p hat, then what we're going to do is make p hat, q hat the biggest that we can make them, That's 0.25 over our error squared. All right. And I want to be clear, just like we did before, if it's not a whole number, we round up to the next larger whole number. All right. A federal report indicated that 24% of children under the age of 6 live in poverty in Montana, an increase over previous years. How large a sample is needed to estimate the true proportion of children under the age of 6 living in poverty in Montana within 1%, with 90% confidence? All right, so let's talk about what we have. This is our p hat, which means our q hat is 1 minus that. We have an error of 1%. That is right there. And we have an alpha based on our confidence level of 10%, which means alpha over 2 is 5%. Let's see what we get here with that. So I'm getting that that's about 1.64485. So we have all of our pieces, so let's put them all together. And I'm going to be using the top one because p hat is known in this case. So I'm going to put 1.64485 squared times 0.24 times 0.76 divided by 0.01 squared. And let's put that in our calculator. So here we go. So I'm going to square that, the 1 point to the previous answer there, times 0.24 times 0.76 divided by 0.01 squared. Ooh, quite large. Remember, again, we're going to round up. So this is about 4,935 children. To be 90% confident that we're within 1%. Pretty cool stuff. All right, so we need to keep this in mind for this next problem, this whole thing here, for the next one. All right, so here we go. Of the 71 subjects in a study about abstaining from smoking for 8 weeks, a 95% confidence interval of 0.5981 to 0.8104 is constructed. Use that statement to find the point estimate p hat and the margin of error e. So what they are saying here so we are here. Let's fix that a little bit better. 0.5981. Now we also know, again, from the definition up here, the yellow there, that p hat, which is one of the two things that we're looking for, minus e, and then p hat plus e are here. What does that mean for us? That means that p hat minus e equals 0.5981, and p hat plus e is 0.8104. And if you remember from your algebra class, this is what's called a system of equations. And you learned two methods to do this, substitution method or the elimination method, which is the method I'm going to use right now. Because I notice when I add the negative e plus the e, they go away. P hat plus p hat is 2p hat. And 0.5981 plus 0.8104 and give me 1.4085, which means p hat is going to be half that, so divide by 2. 0.70425. So there is one of my two answers. There's my p hat. And I'm now going to plug that into this bottom equation here. So 0.70425 plus E equals 0.8104. And when I subtract that to get E, 0.8104 minus 0.70425, I get that E is 0.10615. So there is my margin of error. I hope you found that helpful.